Questions. So let's take a look at any questions we have, and then we'll take a quick look at 6.6 with differentials. So any questions or anything we want to go back to right now? Okay, I don't see anything popping through. So let's go ahead and take a quick look at 6.6. So the concept of differentials, we're going to connect this to our circle problem that we did just a minute ago. So when we looked at, I'll take us back to, hopefully my picture kept, this one with our two circles where a little bit of change from a small circle in terms of our radius, a little bit of expansion produced a little bit of gain in area. And the same expansion on a larger circle produced a larger gain is the idea of a differential. Here, we can talk about a little change in our radius produced a little change in our area. A little change in our radius produced an even bigger change in our area in our second situation. So when we talk about differentials, the idea behind dA dt, or sometimes if we're talking about dA dr, in this case, will be kind of what we look at, then either the top or the bottom on its own, in either case, are each a differential. So we talk about the derivative and we say differentiate something, but the individual components, the dA and the dr, are called differentials. And if we're thinking back just a moment to dy dx, dy is a differential, dx is a differential. And I want to connect this idea of a differential and the dy over dx together, telling us the derivative is related to the instantaneous slope. We say dy dx is the instantaneous slope. So I want you to picture for just a second like an equation y equals f of x. If you pick a point, at this particular point, we could determine the derivative. So if I just sketch in a really rough sketch, that red line is a tangent line to the curve at the purple point. Now, when we are looking at adding a second point, say I add a second point over here. If I were to connect these two, I have a lot going on right now, but in terms of kind of separating this out so it looks a little better in our picture, if you just focus on the 2 points in your triangle, think about what we would call the vertical component our rise, or the change in our y. The horizontal our x, or our change in our x. And that dy dx would give us a slope approximation between the 2 points, or think about like a secant line there. So our dotted here represents a, change in x, jumping ahead here. That dotted line is a change in x. And then this entire dotted line for the y is our change in y between our purple point and our blue point. Now, in terms of what a differential does, this idea of a differential is related to the tangent line or to the derivative. So for a differential, instead of delta x, we change to dx. And instead of delta y, we change to dy. But the dy that we look at is going to be controlled by that slope line. In other words, the dy, instead of going all the way up to the function, goes to the derivative's approximation. In other words, the derivative is showing what's happening at the function at that point. And so this piece, the orange piece, that piece is the dy. Now, if I were to take my triangle and instead of going so far over from the purple to the blue, I were to condense it in, think about in this case, if I go from bottom to function, that component is delta y, the change in the y. And if I go from the bottom to the tangent line, that is our dy. So in this case that we're looking at, this one, our delta y and our dy are closer together than in our first example. And the closer you get to the original point, the closer and closer they get to each other. What we say is that if you have a small enough delta x, in other words, it's teeny tiny, then you can swap delta x and dx and delta y and dy. So for small delta x slash dx, and I suppose I should be careful. My slash here is just trying to say or, because notice in the picture, the dx and delta x are the same. Right? It's really the dy and the delta y that are different. Our change in y is close to the differential in y. And I like to think about a differential as something small, and it's a small amount, but it's the amount that I increase. So think about kind of trying to change our language in the picture with this one. We have a differential that's pictured by the yellow ring and a differential that's pictured by the purple ring. Changing by a little bit produce this size differential. Changing by a little bit produce this size differential. So when we're taking a look at specific problems, we are going to think about some sort of context. For example, suppose we have a circle. Change this to a different color here. So suppose we are producing circles, and let's call them a disk, like we're producing some sort of disk, like a solid disk, like a washer. So we're producing a disk, just like two-dimensional. We won't go into volume here, with a radius of 5 centimeters, so about 2 inches. So not quite a CD, but like a donut, a flat donut with no hole if we're talking a disk. So suppose we're producing a disk with a radius of 5 centimeters. But let's imagine for a second that our machine is off. So if our machine is miscalibrated, our machine might be off when it is selecting the radius to use. For example, if we might imagine like a circular cutting machine, I don't know if you've seen, can visualize what I'm talking about, but let's say our machine is going to cut a circle. It might start in the middle and it uses its arm to cut it. So what it's doing is it's using the radius that's selected, the calibration on the radius, to cut that circle. So let's say this machine is miscalibrated and the radius is off. And this radius is off by, let's say, 1/10 of an inch. So I'm going to write that as, let's say the error in the radius is up to 0.1. Oh, and I said centimeters to start. Let's do 0.1 centimeters. So if we think about this one, or we could say like 1 millimeter, but let's kind of keep it in centimeters so we don't have to change our units back and forth. What we want to know is, how is that error change going to affect the error in the area? In other words, if you're off on one measurement, they're related. We can think about being off here is going to cause my bigger picture to be off. And that's the idea of a differential. A small change here can affect my ring differential quite a bit. Think about your picture. If this little amount on our wing, you guys can see there and here, represents like 1/10 of an inch. You can see that if we're producing a small disk, we're going to get some error, but if we're producing a bigger disk, that error is going to be even bigger in terms of area. So what we want to know is how much error, sometimes they'll phrase this different ways, but how much error should we expect in our area measurement? Now, one way to do this is to just do it directly, to kind of say, okay, well, that's 4.9 to 5.1. Like, what does that look like? But another way to do it using differentials is to think about your geometry, calculate the differentials, and use these measurements as differentials. So in other words, this 0.1 is a differential, and it's a differential on the radius. In other words, the radius is 5 centimeters, and the differential or the error on the radius is 0.1. If we think about the relationship between the area of a circle and the radius, we get this equation. Now, even though it's related to our ideas and implicit differentiation, we're not going to take the derivative with respect to t. We're just going to do dA dr. Kind of that first step that we were doing in the previous. So if you have dA dr equals 2 pi r, this means that the dA, if you're just solving for the dA, think about this like a fraction. If this were 2/3, you could multiply through by 3. We're going to think about the dA and dr as separate entities, separate things that we can separate out. So what we're going to do is go ahead and write this by multiplying our differential on the bottom over to the other side. So dA equals, or the differential of A, equals 2 pi r times dr. So notice what you actually see here is it's not just how much error, but it's actually how big the radius is. Being out further is going to give you a larger error than when your radius is smaller. So let's actually calculate it in this case. So in our case, we have dA equals 2 pi times 5 times 0.1 centimeters. And I'm going to drop this into Desmos with the pi so that I go ahead and get a decent approximation. So I'm going to type in my 2 pi times 5 times 0.1. Now, if we calculate that out and maybe think about the answer that we're getting, I got 3.14. Well, that's pi. Well, take a look at your numbers. I should circle them in a different color. 2 times 5 gives me 10 times a 1/10. 10 times a 1/10 gives me back 1. So you're really getting 1 pi or pi. And your differential for your area is 3.14. Now be careful here. I'm going to go below. It's 3.14, but it's not just centimeters, it's square centimeters because our area units matter. So what this is telling me is I could expect up to about 3 square centimeters off in my materials. Because if you're trying to figure out, well, I know I miscalibrated, how much more materials am I going to use up? If you're consistently getting too big of a radius, you're going to consistently use too much material. So you're going to see questions kind of like this. Now, some of the other types of questions, they might just give you a function. Like they might give you y equals, you have one in there that's something like y equals x squared plus 2x. And instead of giving you this part, they just go ahead and give you either a delta x or a dx, like a 0.1, and then they ask you what is dy. So in this case, when there's no context, we're just thinking, okay, you can always swap a delta x for a dx. And then when we're figuring out our differential in this case, we can calculate our dy dx really easily from what's going on. Here, we could say 2x plus 2. And then we can think about splitting this up. I would probably go ahead and put my 2x plus 2 times dx. But then if I know my differential, they're also going to need to tell you your x value to be able to finish the problem. But if they tell you your x and your dx or delta x, then you can find your y differential. So I like to think about differentials as telling me error tolerances. If I change a little bit in one unit, how much is it going to affect the dependent unit? If I change the radius a little bit, how much is it going to change my area? All right, so questions on this one. All right, so I think for your differential section, there's a few where they give you kind of warm-ups with no context, kind of like the second one we did. And then you have a circle, and then I think you also have a cube that kind of branches off the cube that we already did, ties in there. So in terms of homework, let's just kind of go back and summarize, and I'll open it up for questions here. For your homework, if you're watching with us live, Grant, you would only need to go through and do the last blowing up the balloon because we went through the other two together. But if you're watching this recorded, you would need to do both of those ones, the water line, the 2 rates, 1 relationship, and then blowing up the balloon. All 3 of those Desmos activities that are new. And then you would also need to do your MyMathLab homework. Again, try to do that blowing up the balloon before your MyMathLab. That'll make things a little bit smoother. All right, so any content questions on our new stuff? So let's talk about just our big picture and what to expect in terms of the test, because this is our last section in chapter 6. So if you've got a calendar handy, you might want to look at it. We'll talk about next week and the following. So normally when we finish up content, I'm trying to give us a day of review. I'm going to try to continue to do that so that we can ask our questions, we can clarify, we can work some homework problems on Tuesday, whatever we need to do. So on Tuesday, April 7th, next Tuesday, that will be our review session. So if you're watching this recorded, try to send me all your questions by Monday, like the end of the day Monday. So that on Tuesday morning, I can look through those and add anything I need to our review or kind of modify it based on the questions you have. Don't be afraid to send me the MyMathLab Ask My Instructor questions. I'll just pull those straight from what you send me and work through some of those if those are the requests. Or if you just want to see more examples of a certain type, let me know. Then what I will do is open up your chapter 6 test probably Tuesday evening after I go through and just make sure everything's ready to go. Maybe even as early as 3 o'clock, we'll just see. But Tuesday evening, your test will open. And then normally, if we reviewed on the 7th, we would test on the 9th. So I want to leave your test open, and the rest of the week would be like taking the test. That's what we would do in class. So if we look ahead to the next week is actually part of our spring break with Easter. So I don't see you on the 14th because that's part of our Easter break. And then we do have class on the 16th. So what I'm going to do is open up the test on the 7th, but I'm going to leave it open through the 15th instead of like closing it on the 10th. That way, if you are using your spring break to catch up a little bit, if you're kind of adjusting to all of your schedules, everything being online, it's totally fine. We'll kind of close at midnight on the 15th. That way, when we come back on the 16th, we'll be in chapter 7, which is our last chapter of contents in our last unit. Let's see. Other questions here? Other thing I just thought about that I don't think I said specifically, the rules are going to be the same as for the last test. So part of the reason is, I know this is not, even if you're watching this recorded, it's not the same as being in person. It's not the same as you guys getting to work these out. and getting to help each other understand. So I think in this case, we're going to have our test be open notes as well. So the same rules that you had for the Chapter 5 test, you can use your textbook, your notes, any problems that you've worked out, but no live sources, meaning no Googling for answers, no looking at things like Symbolab, but any resources that you've kind of compiled. So really try to make an effort to go through your notes, write down the examples, write down the homework problems that you're working out so you can use those on the test. All right, so other questions here? And for the related rates and differentials, I really am going to stick to, you'll see on the test, or on the homework, excuse me, kind of a narrow range. The geometric problems are going to be circles or spheres or cubes. And then I threw in a couple of application problems where they're not circles and cubes, but they give you the function that you should implicitly differentiate. In other words, you don't have to come up with the function in that case. You just have to implicitly differentiate and plug in. So those are a little bit different. If we have any questions, we can take a look at those on Tuesday as part of our review. But after you've done these ones, those should be pretty straightforward as well. And then kind of same thing for the test. There's lots of stuff in 6.5 with ladders and triangles and all kinds of other dimensional shapes that we're just gonna leave alone for right now. All right, so it looks like we don't have any other questions. What I'm going to do is go ahead and end our meeting and get this posted for those of you who are watching it recorded. Let me know what questions you have. In terms of homework due date, that will also be like the 15th. I think I put that on there. I'll double check to make sure I have that right date on all your Mind Math Labs for this unit. I didn't have any old dates on there, but we'll kind of have everything due that Wednesday before we come back from Easter break. All right, guys, so I will see you virtually on Tuesday or send me an email with your questions. All right, have a good day.